Hello and welcome to another video talking about networking gear. In the previous video for the UDM Pro MAX firewall, we looked at the performance of that firewall, particularly related to throughput, so measuring the peak traffic capability, both going through the firewall and coming back in. And we looked at the performance of it with the standard configuration, as well as if you turned on the intrusion detection and the deep packet inspection. And that performance was as expected. It's nearly line rate for normal operations and very close to the advertised 5 gigabit for the incoming traffic going through the IDS and packet inspection. But many people on that thread asked about what was the additional latency of those different configurations. And it got me thinking a little bit about how we could measure latency. And obviously anyone familiar with networking is familiar with using a utility called ping. And with ping, you can send a message from a server to a remote server using a protocol called ICMP. And within ICMP, there are two defined messages for this particular use case, an echo request and an echo reply. And you can send an echo request to a remote server. And if configured correctly, that server will send back an echo reply. And the ping utility will send the echo request to a destination and then wait for the reply to come back and then time the difference from when it's sent to when the packet comes back and use that to compute the round trip time from sending to receiving. So it does give you a view of the latency, but it gives you a view of the latency with a single number that is really the summation of a number of different things. It is a summation of course, the time from when the kernel decides to send a packet to when it actually makes it out the wire. So that includes the network driver. Of course, the wire transit time and any gear in between. And then eventually the receive time on the other end. And then the time for that IP stack to process it. And then of course the IP stack or something on that machine has to decide to send back a new message. That's a reply message. So that gets generated and then sent back into the network driver, which eventually makes it back to the card itself and then out the network, then through all the network stuff you're measuring, then back to you, then through your IP stack, and then back to ping so you can measure the difference. Now, fortunately, ping as a utility is in many operating systems, in the case of Linux in particular, it uses timestamps that are put on by the kernel. So in other words, it doesn't measure the time from when it decides to call the kernel, but it asks the kernel to timestamp when the ICMP packet is about to leave. And then when the return ICMP comes back in, it timestamps it there as well. And so it uses a feature in the kernel where you can out of band get those timestamps, which means that you aren't really taking into account the time it takes to go from kernel mode into user mode to the ping utility. And that's very helpful because it makes the numbers you see in ping be a little more consistent, because if the machine is busy or the ping process is scheduled to a different CPU, you won't see those extra latencies of things moving around. Another advantage of ICMP is that on the other side, on the server side, in this case with Linux, if you ping a Linux server, the ICMP reply generation happens inside the kernel. So there's no user mode activity involved with that. There isn't a user mode daemon that does that reply. It's built into the IP stack. And that means there's no kernel mode, user mode stuff at all involved on the other side. So that eliminates a little bit of the variability. So now you're left with really the kernel mode IP stacks on both sides, plus the interface into the network adapter and the network adapter driver, and then of course the network of choice that we're monitoring. But even with that sort of good thing about ICMP, you still are measuring the entire round trip time. You're not able to measure the speed in one direction or the other. And so if the connection is in any way asynchronous in that speed, if one direction is higher latency than another, you won't know it. They're all added together. So I wanted to brainstorm how could we measure more point-to-point latency. And of course, there are some excellent tools you can buy. There are devices you can hook into Ethernet lines to mirror the Ethernet line, and there are some special ones that do effectively zero latency. So they implement something where they mirror it almost as the bits go by. And so with those, you could, in theory, measure a precise network traffic transit time very precisely, but you need some hardware for that. And that hardware is much more expensive at 10 gig than it is at 1 gig. So I thought, well, is there a way to do this with just some computers that I have? And so if you have a computer and then a second computer, and you want to send from this computer to the second computer, and you want to measure the time it takes to get there, but not the time back, just in one direction, then you need an accurate clock on both of those systems that is synchronized really to each other. They don't necessarily need to be synchronized to an atomic clock somewhere in the world, but to each other they need to be relatively accurate. And so the question is, well, how accurate do they need to be? And so, if you think about a 1 gig connection, the time for a packet to be transferred at 1 gig, maybe around a microsecond, could be a little more depending on the size of the packet. At 10 gig, it could be 100 nanoseconds up to a microsecond or a microsecond and a half. So we're looking for resolution in that microsecond range. And so if you set up 2 computers and you run NTP on them, the network time protocol, and even if you have your own time server, and I have my own Strata 1 time server in my home lab, you can get the machines pretty synchronized, but by pretty synchronized, we're talking in the millisecond range accuracies, and the clocks will be synchronized within a millisecond or a few milliseconds if you get it really well set up and tuned. There are a few things you can do to make it a little better, but fundamentally you're in that ballpark of a millisecond-ish accuracy. And that would be obviously insufficient for measuring latencies of a microsecond or a half a microsecond. And so it turns out that there's another protocol called PTP, which is the Precision Time Protocol. And Jeff Geerling did a really cool video, and I'll put a link to it in the description, about setting up that protocol on 2 Raspberry Pi CM4 boards. And the CM4 boards are unique in that the NIC on those boards supports a feature that's really called hardware timestamping. And it's where the NIC itself can have an internal clock, and it can timestamp packets before they are transmitted, and then also read those timestamps and do the reverse on the other side. And so certain NICs support that timestamping feature. There's a very easy command you can run with ifconfig, and we'll run it on my machine over here later, that can tell you if the NIC supports it. It seems like a lot of NICs do now support that. I think in the past there weren't as many. But those 2 NICs on the CM4s do support that feature. And then there's a second feature unique to the Raspberry Pi world, is that there is a output pulse clock from the NIC that you can map to a pin. And so Jeff mapped both of those devices, had an output to a pin, and he was able to put them to an oscilloscope. So you could see how synchronized those 2 clocks were. And he then ran the PTP software on both of the machines, and it's software designed to use the network interface between the 2 machines. So you can have a cable between the 2 machines, and it uses the hardware timestamping to do very, very high precision synchronization. And he was able to get the synchronization clock to be within like 10 nanoseconds, maybe 20 on a statistical error, but in that ballpark, so exceptionally accurate. Now that is just synchronizing the clocks on the NICs. And you could then use those clocks to do tagging, but I wanted to actually make sure that the system clocks on the machines were also synchronized. And it turns out you can also run another P2P program that can synchronize between the system clock and the NIC clock. And so you can take one machine and have the system clock drive the clock on the network adapter, and then the network adapter synchronization will make the other NIC relatively close to that clock, and then you can synchronize that system clock to the local NIC. And the total synchronization can be, in the order of 70 or 100 or 150 nanoseconds. It kind of depends on a couple different variables, but certainly within the realm of 200 or 300 nanoseconds of synchronization, which is really, really good. And given that we're looking for that kind of 1 microsecond accuracy, or maybe a half a microsecond accuracy, being able to have the clock synchronized within a couple hundred nanoseconds would now enable us to do that measurement. And so I set up a little test rig to do that. And so let's go take a look at what that looks like on the software side. As we're going over there, I'll show you what the hardware looks like. And then we'll try to do some measurements. And the goal really is to measure the latency of all the network stack stuff and everything it takes to get something out onto the network. And then sort of subtract that from the time going through both a switch, across VLANs, and then of course through the firewall. And then we can get some really accurate or reasonably accurate measurements of the latency going through different devices. All we're using really off-the-shelf hardware, at least if your NICs happen to support this hardware timestamping. So let's go take a look at that and see how it's gonna work. So these are the 2 machines I'm using for testing. And so they have a link between the 2 machines that's doing the PTP synchronization for the clocks. And then there are 2 fiber links that go over here to my little test harness. And so this allows those 2 machines to either be on a switch. I can connect them directly to each other, do VLAN to VLAN, or also go through the firewall. So you have one inside and one outside. And so that's sort of the hardware. As I said, it's pretty simple configuration. So let's go look at the software side. So let's take a look at how we're going to do this latency testing. So I have two machines here. You saw them when we walked over here. This is the machine sort of on the inside. This is on the outside. I'm not going to walk through all different test scenarios individually because it's a little time consuming, but we'll do sort of one of them here. So right now this box is on the inside of the firewall and this box is on the outside of the firewall. And I mentioned that one of the things we want to do is have the time synchronized between the two boxes. And so we take a look here. This is running the PTP agent in master mode on this machine. And then on this machine, it's running the PTP agent in the client mode where it connects to whoever the master is and it synchronizes between these two machines. So this basically guarantees that the clock on the NIC here is synchronized with the clock on the NIC on this machine. And it tells you here the error, this plus minus here, is the error in nanoseconds between each one of its measurements. And then it's slowly tweaking the clock offset to try to keep it in sync as possible. And it is generally within 50 or 60, 70 nanoseconds. I think the average ends up being maybe 25 when I let it run for a little while, with occasional jumps of 60 or 70. You can see one there, minus 67. But certainly well within the range of the couple hundred nanoseconds that we're looking for. And so this synchronizes the clock between these two machines on the NIC. But then also over here, we have running is this PHC to sys, which synchronizes from the system clock to the NIC's clock. Same thing here, you can see it's synchronizing in real time, modifying the delay slightly because the clocks aren't perfect to keep the NIC clock synchronized with the system clock. And then over here, you run another program that takes the NIC clock and uses it to drive the system clock. And so this makes real-time adjustments to the system clock. You can see how it jumped a bit there when I was changing windows. And so this allows it to keep the system clock relatively close. And usually when this is running, it'll be within 50 or 60 or 80 nanoseconds, kind of in that range, maybe 100. And so combined with the NIC offset, you know, the error is certainly going to be in a couple hundred nanoseconds, maybe 300 or 400 in some cases, but certainly less than a half a microsecond. And so that allows us to have the two clocks relatively synchronized, which is great. And so if we go over to the first machine, so let's try a ping, 10 pings. And again, this is going from this machine to this machine through a firewall. And so we'll see an average time of 271 microseconds. So which is not terrible, but not great. But what's interesting is if you add, we'll do maybe 1,000 packets, but we'll add this I0. The I0 means that it's going to wait 0 delay between when it receives the reply and starts the next request. And so basically it'll ping as fast as it can, doing one ping at a time. And of course, now you notice it's only 74 microseconds. So the latency went down significantly at higher load, at more packets. And there are a couple reasons for this. One is that the drivers themselves usually coalesce interrupts, meaning that if they have a packet that comes in, they'll wait a little bit to see if another packet is on its way in to avoid interrupting for every single packet. And that's somewhat critical for really high bandwidth stuff. But the result is there's always a little bit of a delay waiting for another packet, and it has a timeout. Eventually it says, well, nothing's arrived, so I'll go ahead and pass this up to the software stack. And that happens in a couple different places where there are some buffers. And it's kind of well known that when you have buffers, you can occasionally add latency because you're waiting for a buffer, or your algorithm will wait a little bit before it sends to the next stage. And so sending them slowly gives you very different numbers than sending them quickly. And it's even true on the switch side, it seems to be slightly different. And that may be based on how the switch is caching, where it remembers what MAC address goes to which particular port. So it's important to have the packets go relatively quick. So now the question is, how can we do this actual measurement of individual latency as opposed to just this round trip? And so we're going to go to a different window here. And we're going to start by capturing with TCP dump on this interface, just ICMP. We're going to save that to a file called send. And over here, we're going to do it to a file called receive. We're going to go back here, over here, and we're going to do that same ping, 1,000 packets, fast as we can go. 79 microseconds average time for it to do the ping. let's go back to the capture. We'll stop the capture, and sure enough, we captured 2,000 packets, which is perfect for 1,000 pings. Over here, 2,000 packets. Now I'm going to copy that file from this machine to the other machine. So now it's here. And I have a little Python script that I wrote that reads the TCP/UDF outputs from both the sender and the receiver with the timestamps, and then correlates correctly which packet corresponds with which packet, and gives you, for every sort of packet you sent and then came back, the sending latency, the receiving latency, and then the turnaround time. And these are based off those timestamps. And as you can see, it's like 31 microseconds was the average latency going out through the firewall to this box, and then 33 microseconds for coming back through the box. And the 7.3 is the turnaround time for the kernel on this box to receive the echo request, make up the echo reply, and then hand it back to the network interface for it to send out. And so this gives you an idea of how you can do those measurements. And let's talk a little bit about what we're going to measure. So we have these two, let me draw a little box here. So we have our two machines that are sitting here, and we have let me put a pin here, we have a connection between the two machines that is used for the time synchronization. And this is a 10 gig connection. And this is dedicated just for the time synchronization. And then there's another NIC here. That's the one we're going to be sort of testing with. And the first test we're going to do is that we're going to put a cable from NIC to NIC. So this is a DAC cable. So it's a direct attached cable, meaning there's a little miniature SFP looking optic here, but it isn't optic, it's a direct attachment. And so effectively the electrical signals on this side are directly mapped into the cable to the other side. And the result is that from the point of view of when the packet is actually transmitted from here to where it's received from here, this is something, maybe it's 50 nanoseconds or 100 nanoseconds. It's a very, very small number with a direct attached cable. And so, over here, we're going to create the ping echo request and hand it off to the interface. It'll make its way across the interface over here. It'll then cause the creation of an echo reply, which will then go back to the interface and then make its way back over here to there. And so we're going to do this test, and we will get a number of like what the time is for the transit across this DAC. But I'll warn you that the actual number we get, though, is really based off of the kernel timestamping the packet here. And then it has to go through all the network adapter code, the sending to the NIC, and then eventually out the wire, and then, of course, across the wire. And then over here, the same thing is going through all of the network driver code and the NIC code, eventually getting to the IP stack to where the PCAP filter will see it and timestamp it. So you're kind of measuring the combination of all of this software latency along with the latency of this cable, which is really, really small. And so we'll do that first to kind of get a baseline. So this is our zero baseline. This is with no gear in the way that measures how fast it is, so you can I have an idea of what the time is for those software interactions. And then we're going to put a switch in the middle. And so we're going to have a switch here. And so now it's going to connect from here to a port on the switch. And then another port on the switch will connect to the other adapter here. You can run the same test, and then this test will give you some time X, and you'll subtract off the DAC time here to get a final number that is the added latency from the switch itself. How much additional latency did it add to add the switch in the middle instead of just a straight cable? And so that'll give us an idea of what the switch adds in both directions individually. Then we're going to do another test where we have one of the ports in a different VLAN. And so the traffic's going to come from one machine in one VLAN. And of course, this is a different VLAN. And what that means is that we're going to have to go VLAN to VLAN. So we have our UDM Pro sitting here. And there is a connection from the UDM Pro to the switch. And this is that LAN port, which is a 10 gig connection. And so now when traffic is flowing from here to here into this switch, it's in the wrong VLAN. So it's going to traverse up the connection, go to the router that does the VLAN to VLAN routing. It'll then come out of that router and go back down that same 10 gig connection over to the switch, and then across the switch to the outbound port, and then all the way back over to the other machine. So now we can take this time and subtract off all the previous times and see what the delta is, which is how much time was added for the router to do the VLAN to VLAN routing. And keep in mind that includes both the time for the routing itself, plus there is a little bit of network interface transit time because you're going up to the router and then back down from the router. So it kind of gives you a summation of how much extra latency is added by going VLAN to VLAN as opposed to just directly across a switch. And then the final test will be a slight change where we're going to take this network interface here and we're going to put it on the outside interface of the router. And that way now when you do your ping test, you're sending up through here into a port, across to a connection to the router, up to the router, through the router's firewall. So now you're going through the firewall, which includes the network address translation, and then out to this interface and eventually back over to the machine. So this will give you another number, and we can of course subtract off the numbers from below and give you the delta of how much latency does it add to go through the firewall, not just the VLAN to VLAN, but the firewall and the network address translation. So we have a good way to measure latency pretty accurately in both directions and to take off the parts of the latency that aren't important to us. So that's what we're going to do. And I went and ran these tests, and I ran the tests with both ICMP and UDP. And for UDP, I had to write a little bit of software to send a packet and then reflect it on the other side and record the timestamps coming back. And the numbers are very similar. So let's look at what the results were, because that's what really matters. And so we'll start with ICMP. So this direct connection is just that DAC cable connecting between two machines. As you can see, we measured 14 microseconds of latency. And keep in mind, this number is here because it also includes all the time for the software stack from the moment it is tagged and timestamped to when it goes into the actual network driver, gets transferred to the card, and eventually gets transferred out the NIC to the other side. And so this outbound number includes all of that latency, and the same for the inbound packet. That's the one going the other direction. So it includes that software side on both sides. And so these numbers are kind of the zero number. You really can't get below this because this is just a direct connection between machines. So we can use this as the baseline to see what the additional time is for the other use cases. I also mentioned the round trip time, which is the round trip time from the packet capture. The turnaround time is how fast the ICMP echo was created after the reply was received. As you can see, it's 7.2 microseconds. And one good thing about ICMP is that ICMP, in most cases, of course in Linux this is true, the echo reply is generated inside of the kernel. So there's no user mode interaction. So when the request arrives, the kernel generates the reply immediately and sends it back. And so it's a relatively low turnaround time. So about 7 microseconds inside the Linux kernel for it to generate and send the packet back out to the wire. And this user mode is what the ping program itself reported. And so you can see it reports a slightly higher number than the measured here because this includes everything going up to the ping program, getting the numbers from the kernel driver and displaying them. So good numbers, good baselines. It gives you kind of a ballpark number of what kind of latency there is just in all the software stuff to get a packet from a piece of software out to the NIC and then across something. So then we add in the switch. This is putting a switch in the middle. It's a MikroTik CRS 326, which is a nice switch that has 40 gig QSFP plus a bunch of SFP pluses on it. And you can see that it's only slightly longer. And I have the delta here, about 2 microseconds of latency in the switch if you add the switch in. And that number is reasonable. I think if you kind of look around, you'll see people talk about numbers on cheap switches could be 5 microseconds. On cheap 1 gig switches, you'll occasionally see 30 or 40 microseconds. Lots of switches you'll see in the 1 to 2. There are some fantastic, very fast switches that will have latencies in 300 or 400 nanoseconds. There are some ultra high speed that'll be even faster than that. The biggest limitation on the speed is that you need enough time to at least get the MAC address transferred over so we can see the MAC address. But that's only going to be at 10 gig speed, maybe 10 or 15 nanoseconds. And so it's possible to make them very, very fast with a lot of extra money being spent. But with most normal chipsets, this kind of number is perfectly reasonable. So we're adding 1.8 microseconds of latency, adding the switch, starting out with the 14.6 just for the software stack and the network interface. So 2 microseconds added for the path across the switch is a pretty reasonable number. The next line is the VLAN to VLAN. A reminder, this is going to the switch, then up to the router, across the route interface for VLAN to VLAN, back down, and then back out to the machine. And you can see this number is quite a bit bigger. It's added about 14 microseconds. Part of that, of course, is just the transit to the UDM Pro that wasn't there before. But the majority of that is in the UDM Pro. That's the router itself routing, looking at the packet and deciding it needs to go to a different VLAN. Of course, there are VLAN to VLAN firewall rules it has to check first. And so all that happens, and you have a latency added of about 14 microseconds. And put that in more clear ideas, that means the VLAN to VLAN is similar in latency to maybe 7 switches worth of transit. It's 14 microseconds. If you consider that the connection before direct was about 14 microseconds, it's about twice as much latency. So it kind of gives you an idea of sort of the ballpark of what a VLAN to VLAN transition is like in terms of latency. And then the next step was going through the firewall. And you'll notice that the numbers are a little higher, but the delta isn't that much. The firewall itself, on top of the VLAN to VLAN, only added 2.5 microseconds in that direction and a little less than 1 in that direction. And so that's partially because, of course, the firewall and the VLAN to VLAN are both technically routed. The big difference is the VLAN to VLAN doesn't do NAT normally. It does do firewall rules. Meanwhile, the firewall side is doing both the checking of firewall rules and also the network address translation. But it's a pretty small penalty. It's only an extra switch's worth of latency for the firewall versus the VLAN to VLAN. And then I put on here the comparison of the firewall to just a switch by itself. And so you can see we're adding 20 microseconds or so. And keep in mind that this is a firewall, and typically this might be used going to the internet. So you might ping someone, and your ping, if some super, super fast close thing is 2 milliseconds, right? This is going to add, instead of 2 milliseconds, you're going to have 2.02 milliseconds. So it's a very small additional latency relative to real world internet latencies. Now, inside of a small environment, inside a local environment at very high bit rates, that's a number that makes a difference. But on the true internet side, if this were actually 40, twice as much, it would be very difficult to ever even be able to detect that in real internet usage. So looking at UDMP, the numbers are very similar. They're a little slower on the firewall side. I think there's a little more work being done there for packet inspection. You can see it's about 5.7 microseconds on outbound, not as much on the inbound. And I did notice in looking at the actual data logs, with UDP, there's a little more variance. The first couple hundred packets were a little slower, and then it kind of sped up a little bit, which could be some optimization in the code inside of the firewall, and also could be things like caching certainly can make a difference. But overall, similar numbers with UDP. The one big difference is the turnaround time is much more, because over here, this turnaround time for ICMP is the kernel doing it. This over here is actually going up to a user process, which receives the packet, then sends back a reply. And so there's a user mode transition, so you'll lose a little bit of time there. But overall, though, the measurements they're really good and interesting. I think it's good to think of VLAN to VLAN in terms of it's equivalent to maybe 7 switches worth of latency, and with a firewall, it's a little bit more. It is interesting that the firewall difference isn't that much more than the VLAN to VLAN, which is certainly a testament to the hardware being able to do all the network address translation very quickly. I have not dug deeply into doing these same measurements with the IDS and packet inspection terminal. I did do a quick test, and the IDS on outbound inbound did add quite a bit of time. I think it was more like 42 or 44 microseconds, so quite a bit more time. And that's not surprising, because it's probably doing a lot more checks and actually looking at the data inside the packet. So you'd expect there to be a little more slowdown. But I'll do a video later about testing the latency with those additional features. I'm going to try to maybe test a few other firewalls as well. But in summary, though, it's a really interesting way, this idea of using 2 machines and accurately synchronizing their clocks is a great way to measure latency and to be able to measure it sort of in each direction. I've spent quite a bit of time doing lots of different tests. I did one that was over 100,000 packets and multiple times in a row, and the numbers were always very, very, very similar. So the clock synchronization certainly works. This is not going to give you accuracy of 100 nanoseconds or 10 nanoseconds, but in these microsecond number ranges, I think it's reasonably accurate. For the devices we're talking about here, the more HOMELAB devices, I think this is a pretty neat way to be able to measure latency. And the numbers were interesting. I wasn't sure what it was going to turn out to be, but 2 milliseconds for a switch feels about right. So let me know if you have any questions, put them in the comments, and I will follow up probably with some more latency and bandwidth testing on some different firewalls here over the next couple of months. Thanks for now.